Graphing logarithmic functions. A table of values for y is equal to log base 10x is given below. The values are given to one decimal place. So if we sub x as 0.1 into the equation, so replacing that x with 0.1, we get an output or a y value of -1. Subbing in 1, we get an output of 0. Then we get 2 comma minus 0.3, then 3 comma 0.5, and 4 comma 0.6, and 5 comma 0.7. And then plotting them on our graph, we get this curve. So this is the graph of y is equal to log base 10x. So the domain, so the inputs are the x values. So we only have up as far as 5 here, but the domain is the real number line, just the positive part. And the range is the entire real number line. So the range would be the outputs. So that is the entire real number line. The diagram on the right above, so this diagram here on the right, illustrates that the inverse of the exponential function y is equal to e to the power of x is the logarithmic function y is equal to log base ex. So log base ex is generally written as ln x. So log base ex is generally written as ln x. So we can see we have log base 10x. So this time it's actually in blue. So it was in red on the first graph, and now it's in blue in the second graph. And what's colored in red is y is equal to 10 to the power of x. So that's the red curve. And we can see that the line y is equal to x is a mirror line in between the two curves, and it goes through 0, 0. So the points on this line would be 0, 0, 1, 1, 2, 2, 3, 3, and so on. And also obviously -1, -1, -2, -2, -3, -3, and so on. So the line y is equal to x forms a mirror line between the two functions. So in this graph, the red curve is y is equal to e to the power of x. And the blue curve is y is equal to ln x. So remember from the previous slide that ln x is log base ex. So, and again, we have the same mirror line as we did in the previous slide with the other graph. They look very similar, but they're not the same. They're not the same graphs. The function y is equal to e to the power of x has the inverse function y is equal to ln x. The graphs are reflections of each other in the line y is equal to x. Y equals e to the power of x has the x-axis as an asymptote. So that is the red curve. So the x-axis is an asymptote. So the curve gets closer and closer and closer to the asymptote, but it never actually touches it. Y equals ln x has the y-axis as an asymptote. So the y-axis this time is the asymptote. So the curve gets closer and closer and closer and closer to the y-axis, but it doesn't actually touch it. For y equals e to the power of x, so for the red curve, the domain is x is an element of the real number set. So the inputs, or the x values, are the real number set, the entire real number line. So positive numbers, negative, fractions, decimals, irrational numbers. And the range for the red curve, so y is equal to e to the power of x, the range is y is an element of the real number set, where y is greater than 0. So we can see that the red curve, it never goes below the x-axis, because remember the x-axis is an asymptote, so it just gets closer and closer and closer to the x-axis but never touches it. So it doesn't actually produce any negative y values. And it doesn't have a y value of 0 either, because remember it never actually touches the x-axis. So it'll never have a y value of 0, but it will have everything above that. For y is equal to ln x, so that's our blue curve, the domain is x is an element of the real number set. So the domain, so all the x values or inputs are the real number line where x is greater than 0. So in the same way, the x values are never going to be negative, and they're never going to be 0 either. Because remember, this blue curve is getting closer and closer and closer and closer to the y-axis, but it never actually touches it because the y-axis is an asymptote. So it never actually touches that invisible line. So therefore, the x values will never be 0, and they will never be any of the negative numbers on the negative part of the real number line. So there will never be any negative x values, and there will never be a 0 for an x value either for this blue curve. And the range of the blue curve is y as an element of the real number set. So the range, the outputs, will be the real number line. So again, positive, negative, whole numbers, fractions, decimals, rational numbers, and so on. E to the power of x is positive for all values of x. So that going back to this red curve, so e to the power of x is positive for all values of x. And ln x does not exist for negative values of x. So this blue curve, so ln x does not exist for negative values of x. Note, the inverse of the function f of x is equal to e to the power of x may also be found algebraically as follows. So if we start off replacing f of x with y, so we have y equals e to the power of x, then we get the natural log of both sides. So we apply the natural log to both sides. So we stick on ln in front of y, ln representing the natural log. And then applying the natural log to the right-hand side, so applying it to e to the power of x. Well, the natural log, so ln, is the inverse of e to the power of x. So we know that from our statement at the top, and it is something that you should learn off by heart. In your calculator, you will see the ln button, and then when you press shift, you get the e function with a little square. So that's a way that you can remember that they are the inverse of each other. They're like the opposite of each other. So y is equal to e to the power of x is the inverse of y is equal to the natural log of x, so ln x. So when they're applied, they kind of cancel each other out, and you're just left with what the power is. So in this case, the power is x, so you're just left with x. And the natural log of e is equal to 1. So that would come up into your calculator if you just want to check it out. So ln e, and then your power for e would be 1, would just give you 1. If you want to try out a few different ways just to prove to yourself that this is true. So if you input ln bracket e to the power of 3, for example, you will get 3. So it's like the natural log and the e, they just cancel each other out, and you're left with the power. So I'll write a couple of examples here on the right hand side. So as you can see here, the natural log of e to the power of 3 is 3. So it's essentially like the natural log and the e, they cancel each other out, and you're just left with the power. Likewise, we can see the power 7, power of minus 2, and then x, which is what we're using at the moment. So that's how we end up with x on the right hand side. But don't forget that we applied the natural log to both sides, because what you do to the left, you do to the right. So it's very important that we still have the natural log on the left hand side, so natural log y. So then we just rearrange them to have the x on the left, and then we apply our inverse. So f to the power of minus 1 is the inverse function of x, and we just swap the y for x. So the inverse function of x is ln x, or the natural log of x. So changing y to x and x to f inverse x as above. So this is just showing that this statement at the top is true. The graph of the function f of x equals a times b to the power of x is shown. Find the values of a and b. So here is our red curve. Notice that it crosses the y-axis at 3, so 0, 3. It has a point 1, 6, and the x-axis is an asymptote. So the red curve is getting closer and closer and closer to the x-axis, but it will never actually touch the x-axis. So we start off with our function. We know from our graph that 0, 3 is a point on our graph, a point on our curve. Therefore, f of 0 is equal to 3. So the x is 0, the y is 3. Likewise, we could say f of 1 is equal to 6, because that's another point we can see on our curve. So the x part is 1, the y part is 6, because 1, 6 is on the graph. So we sub in the x value as 0 into our equation, so replacing the power x with 0, and the 3 is the y value, so that's going to be in place of f of x. So f of x and y is the same thing. So simplifying, so b to the power of 0 is 1, and a rule is that anything to the power of 0 is equal to 1. That is in your indices laws, but it is something that you should learn off. So a multiplied by 1 is just a, so we get a is equal to 3. So we found a, now we have to find b. So we know that 1, 6 is an element of f of x. So 1, 6 is a point on the graph f of x. So doing the same thing, we go back to our original formula or original equation. So a times b to the power of x. We replace the x this time with 1. I've highlighted that in yellow. And we replace f of x, which we know is another way to say y, with 6. So I've highlighted that in blue. So it's the same process as above. We also know that a is equal to 3. So we replace a with 3. So we have 3 multiplied by b is equal to 6. So 3b is equal to 6. So b is equal to 6 over 3. So b is equal to 2. So we were asked to find a and b, but we can actually put them together and create the equation. We weren't asked to do that, but I'm just going to add it in at the end as a final step. So our function is f of x equals 3 times 2 to the power of x. So our red curve is the equation f of x, or the function f of x equals 3 times 2 to the power of x, where a is 3 and b is 2.